Hi, and welcome back to the ETIS Test Lab here in Zurich. My name is Lena, and I do research on MRI implant safety. Today I'm going to show you our newest medical implant test system, the MITS-TableTop, short MITS-TT, which we use for radiofrequency assessment of heating and induced voltage of medical implants. In this system, instead of having a magnetic field that induces an electric field inside the tissue simulating liquid, we use 4 electrodes to directly induce electric fields inside our liquid, in which we place a racetrack with an implant to test the induced heating or induced voltage at 1.5 or 3 Tesla. The voltages across these 2 electrode pairs are generated by 2-channel amplifiers that operate at 64 and 128 MHz. The relative amplitude and the relative phase between these 2 electrode pairs is controlled by the software, and we can apply any polarization we like, linear, circular, or user-defined. The MITS-TableTop comes with the advantages of higher accuracy. It's small enough to fit on this table, it uses small amplifiers, and we actually don't require the shielded room. We have a MITS-TableTop high permittivity and low permittivity phantom. The dual band source, the amplifiers, and the computer are all housed in this rack. And as you can see here, Zurich MedTech's piecewise excitation system fits in the same rack, so we can offer the entire workflow for RF implant safety testing here. Upon start of the software, you have to choose the operating frequency, either 64 or 128 MHz. You also need to choose which unit you are using, the HPM or the LPM. Now that we started our software, we can see here in the top left our frequency of operation, which you can override with a custom frequency. Underneath is the input of the power level. The maximum is 40 dBm, which results in generated E fields of about 60 volt per meters in the high permittivity medium. This is sufficient to perform validation with sensitive dosimetric and temperature probes. Underneath this, we set our exposure polarizations. This can be done if you go back to the top to the menu. There's either the basic polarizations, the pre-programmed TFD polarizations, or completely customizable polarizations. The 4 basic polarizations include 2 linear and 2 circular polarization. And this, depending on what you choose, changes what you see here on the left. Underneath, you can decide if you want to do a timed exposure. So you can set the start time to immediately, you can put a start time that you acquire or a delay on it, and a duration of your exposure. Here, I've mounted the SAMDU test item. I'll place the racetrack inside the MITS-TT now. The test field diversity method, which we've shown in detail in our earlier video, involves making fast point measurements above the lead tip without repositioning or remounting the lead, while we vary the incident field through the different polarizations. Once I turn on the system, the blue light indicates now that the amplifier is activated. Let me choose a circular polarization and start the exposure. As you can see, once the exposure is started, the light turns red. Now I can use DAISY to measure the power around the tip, or a temperature probe to measure the heating. Here we'll capture the point-specific absorption rate, SAR, at 20 different polarizations in real time. These could also be temperaturized or induced voltage measurements. In order to now reliably scale our point SAR to the deposited power, we need to measure the 3D field distribution with a volume scan of 1 highest polarization. This takes about 15 minutes, and hence we speed up the video. For complete implant validation, we now only need to repeat the measurements for 1 second lead path, and then we're done. Now that the volume scan measurement is done, we can remove the racetrack, and then we verify the background E field along a reference line for each polarization. Now that we're done with the incident field measurements of all our 20 polarizations, which you can see here, the scan is done, we can process our data using a Python notebook. The Python notebook is using the test field diversity method, and it's integrated in IM Analytics Lab, which is a part of Sim4Life. So we can here read in our data of the measurement and process it with the notebook to then in the end compare the predicted deposited power that we measured to the target values of the SAMDU, which is part of the latest draft of the 10974 ISO standard. You can see here in the top graph the deposited power for each of the 20 polarizations, and below the deviation of our prediction to the measurement that we just did. And this deviation is under 0.13 dB. Now, comparing this to the previously used test field diversity method, you can see here that we are way more accurate with our measurements. It's obvious from this simple demonstration video that testing is much faster, more reliable, and easier with this MITS-TableTop system. It allows us to test several implants per day and thus has a much higher throughput. Thank you for joining me today when I presented our latest R&D efforts when it comes to implant safety testing.